Hello, testing. All right. Welcome back. Um, yeah. So I just pull out this um, if then argument just for joke, maybe for fun. Maybe I read this. Find it funny. Let's put it up here. This week I got 6 students visited my office hour, which is good. Please, if you have any question, if you try out the even number question, you can check with me during the office hour. Okay. Uh, First of all, any Q&A question from you? Any one of you want to ask question? So in the last hour, we will do quiz. Okay. Only 2 questions, don't worry. Very short. Any question from last week materials, previous week? Okay, I'll give you chance to think to prepare what you want. But I want to tell you something that is actually someone found out some error in my step. If you try, you should know. Last time I distribute around, let me see. Yeah, I distribute around here, so which is wrong. If you can see I will update the lecture notes soon. But you should check that my previous version, I distribute around this junction, which is wrong. You can't distribute around this junction. You only can do associativity. Okay. What you can distribute is distribute around conjunction and disjunction. Okay. So you can let this become your R, and then you distribute. Okay. Also, you also note that actually the distributivity laws that I use here is not the usual one in the lecture notes. You have to modify, you have to use commutativity laws and then distributivity law and then to get into this form. Why I can see so fast is because actually this is just the number system. I mean, not just the number system, but similar to the number system. So you can, when you want to distribute across the multiplication, you can do it at the back or do it at the front. Okay. But for you, you should prove that you can do it. Okay. And because I didn't write down the law, so it's an exercise for you to check to state all the law that I use. So for example, from here to here, I use the double negation law. Okay. So make sure you write down all the law. So in the exam, you should write down this law. So, but it doesn't mean that you need to memorize the table. In exam, I think I will give you this table. Okay. Only this kind of table I'll give you, this table. So it's yeah. So it's these number laws, not number laws, I mean, these identities. Okay. Mm. The other tables I won't give you like this, I won't give you. So this you have to, what you have to memorize is this guy and this guy. Okay. The other can be derived from these two. This is contrapositive. So maybe this. So you need to memorize this. Um, not memorize, but understand and then internalize. Okay. Only this table I'll give you. This is like the, not because that I don't want you to memorize, but sometimes you will get confused with the name. So I'll give you this. But of course, you need to understand all what they are doing inside here. But we will see again in the set theory. So I think last week someone asked me about the similarity between logic and set theory. Actually, they are under the specification of one algebra called the Boolean algebra, which we will touch it on again at the end of the course. Boolean algebra is a generalization of this kind of identity. You have two operations here, and then satisfy this identity. Yeah, there's a generalization of this algebra. What else I have to say? I think that's all. Any question from you or not? Huh? No? What time is it? No question? No question. We will start today's lecture. So we only do quiz on the third hour, okay? Third hour first 20 minutes we'll do quiz. So we'll do lecture first this hour and then next hour. And then after quiz we will continue with tutorial. Okay? No question? Yeah, please stop me if I'm going too fast, okay? Because if you don't have question, I will assume you know, then I will keep going. Yeah. Okay. So today we will talk about proof. Proof is the last part of this logic. And then after proof, we will go to set theory. Okay. So proofs. So today we will look at different kind of proofs and then try to learn some proof techniques. I would say that proof by induction will be very useful for you. Okay. Later we'll see what's the proof of induction. So when we prove something, we need to start from some statement, which assumed to be true. Whether it exists in this world or not, we don't know. But we want to assume something is true, and then we start from there. So these are called the axiom or postulate. Okay, axiom or postulate. Okay, so we assume some statement are true, and then we start from there, and then see what result we can get from those axioms. And we call it theorem if it is a statement that can be proved from this axiom. Okay. Proposition is another word for theorem. Maybe proposition is not so significant result as the theorem, but both we can use. Proof. So proof is the valid. So it's the argument that establish the theorem. Okay, the truth of the theorem. So you need to, if you want to prove some theorem is true, then you need to provide the step and then give me the right conclusion. Okay. Lemma is also one kind of theorem, also less important, but lemma usually is used in the proof of other results. So maybe you want to prove this theorem, you need to prove some small result before reaching this theorem. Okay. It's called lemma. So these are just words, okay? Corollary. Corollary means, so, okay, maybe I draw some chart for you. So maybe it's like theorem. So before proving theorem, you have some lemma. Okay, after theorem, you can prove some easy corollary still. Yeah. So also theorem, but it's something implied by other things. So we call it theorem, call it corollary. How about conjecture? Conjecture is not proven yet. So maybe you try something, you see that it's always true. For the example that you can verify. So you conjecture something. So you think that the statement is true. So you conjecture. and then you try to prove it. Once it is proven, then it's called the theorem. Okay. So this one is like unproven theorem. Okay. So axiom is something always true. This thing is always true. Okay. You take it as a fact. Whether it's existent or not sure, but you start with somewhere. Okay. Yeah. Okay. We will see in example how we're gonna use this thing. Okay. Not the, I mean how we communicate using these words. Okay. Yeah. Okay. Okay. Should I go? I go. Okay. So let's say I give example of proof in number theory. Okay. So let's define some what do you call by a even integer. So so when I say n is integer, right? So n should live in z. Okay. Later you will see this. We will introduce again this symbol here just in a second hour. So we call that an integer is even if there exists another integer such that n is 2k. N is odd if there exists another integer such that n equals to 2k plus 1. Okay, can you see why? So let me convince you by example. Should be proof, but I give you some example to see what's going on. So for example, 4 is even. So 4 is 2 times 2. For example, 5 is odd. So 5 is 2 times 2, 2 times 2 plus 1. Okay, just to convince you, but this is the definition or axiom. Definition or axiom. That I assume is true for at the moment. Okay, so first thing we will do is prove by direct proof. Okay, use a direct proof to prove. So let's see what we want to prove. So the theorem is let m be an even integer, then m minus 1 is odd. Okay, so proof. Okay, proof. So the question say let m be an integer, even integer, then n minus 1 is odd. Okay, so since you already learned the predicate logic, so you can say that this is equivalent to for every m in set m even imply m minus 1 odd. Okay. Okay. So since you want to prove this, you need to check it for every m in integer which is even. So let us take, so we take m, take m even. So by definition, m equals to, by definition, m equals to 2k for some k. For some k. Okay? Okay. Then we want to prove that n minus 1 is odd, right? Then we want to prove that n minus 1 is. That is, there exists some, okay, maybe I don't use k because k is fixed here. So I wrote there is this x in z such that n minus 1 equals to 2x. Okay, is everyone following up to here? I'm just checking the definition. Okay, everyone is following? Following? If not, please ask. Okay, so now we have m minus 1 equals to 2k minus 1. Okay, let me move it to a bigger place. Okay, so okay, so do you know how to get this line? This is by what? By assumption, right? Because we know that m equals 2k. Okay, so I just substitute, right? Okay, but I need to get into this form here, right? 2x plus 1, but this one is 2k minus 1, right? So how? How? Anyone got any idea? I let you think for 2 minutes. You can ask your friend. I mean, discuss with your friend. I give you 2 minutes. How to turn this minus 1 into a plus 1 at the end. Any idea? Anyone got any ideas? Hmm? Any idea? Any breath soul? Any idea? Hmm? You have any idea? Plus 1 minus 1. Huh? Plus 1 minus 1? Plus 1. What do you mean by plus 1 minus 1? From where? The right side? You mean like this? Eh? 2k minus 1 plus 1. Like this? Minus 1. Like this? And then let me see. Minus 1 plus 1 minus 1 like this. Okay, and then you group the minus 1 together, is it? Okay, and then like this. Huh? Is this what you want? What do you want? You want this? What do you want to do? This one? You mean like this? The left hand side. You mean to wait. You mean you mean this? And then okay. No. This I don't want because what I want is so okay. So what this saying is n minus one plus two is odd, but I want to prove n minus one is odd, right? Isn't it? Right. So instead of moving the plus two to the left, I just put it here. Okay, and then I factorize. So then then what? Then I just so we just take s equal to k minus one. Right? Right. So I found this x here. Okay. Okay. Following? Following now? Yeah. Okay. Yeah. So yeah. So originally what I thought is I just pull this two up. Yeah. Instead of plus one minus one, I pull the two up from 2k. Right? I can do this, right? I can pull the two up from 2k. So this one becomes k minus one. Then I also get 2k minus one plus one. It's the same. Okay. Everyone following or not? Okay. Yeah. So yeah. Hence hence n minus one is odd. Okay. So some language you want to learn here is you will use since something then something or mm, so or hence or thus. Um, what else? Let me think. Um, because then I think for now it's forget this. Okay. So this is the word you will use in the proof. Okay. Don't 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 how to say don't ignore this word. Okay. If you ignore this word, then your proof will be very blank. I don't know where's the line following. Okay. Then maybe then also. Okay. Because if then yeah. Okay. Okay. So this is called direct proof because I just start from what are given and then I end with uh the result. So the logic is P implies Q. Okay. I got P and then I prove to you the Q. Okay. So this is this rule of inference. Okay. So got this line here, P implies Q, and then I start with P and then I deduce Q. Okay. This is the rules of inference that I use. Okay. So next. Okay, so this is direct proof. Okay, next. Next I want to show is proof by contrapositive. Okay, let's think of this idea here. So I got the P implies Q first, and then I start with not Q, and then I end with not P. Okay, I end with not P. So let's see. So let's try an example of right contrapositive. Oh, be right here. Same same statement, different way of proving. Then okay, good. Okay, this is equivalent. Is equivalent. This is equivalent to for every n. Then n even implies n minus one. Oh. Ah, okay. Okay, wait, let me move this thing down. Okay, so I want to add an axiom here. Mm, Axiom. Axiom. Every integer is either even or odd. Okay, I think you can prove this, but we don't want to prove it here, so we assume it is true. So I call it axiom here. Okay. Once we got this axiom, then we can consider the negation of this line here. Because if you are not odd, you must be even. Okay. If you are not even, then you are odd. So the strategy is we want to prove by contrapositive. That is uh, showing for every m minus 1 even implies m odd. Okay? Okay, this is contrapositive, right? So I negate and then change the direction. Okay, so we start with suppose m minus 1 is even. We want to show m is odd. Okay, so since m minus 1 is even, okay, by definition, m minus 1 equals to 2 times k for some k, right? Everyone following or not? Okay, by definition. So then m minus m equals to 2k plus 1, which means m is odd. Yes. So sometimes I will put this for the m proof. I'll put. Okay, is everyone following? Any question or not? Hmm? No? Okay. If no, then we continue. Okay, we continue. Huh? Any question? Any question? Okay, next. So next is proof. So okay, let me write 1, 2, proof by contradiction. Okay, so same theorem, okay? Same theorem. So, even integer, then n minus 1 is 4. Okay, proof. So how does proof by contradiction work? So you should yeah, I'll let you see first and then we will see what's going on. So first we suppose m even. Okay. So I suppose okay, wait. Let me write the equivalent statement first. Maybe you will see better. So equivalent to for every m in z. And even imply m minus 1 off. Okay, so we will suppose m even. So we start from the assumption, okay? But to prove by contradiction, we need to negate the q part, okay? So we suppose m even and m minus 1 also even, okay? And then what we are contradicting will be contradicting the assumption. Suppose we assume the result is false, okay? And then we want to contradict the assumption. So suppose m is even, m minus 1 also even, okay? Then I start from the result. Then m minus 1 equals to 2k for some k in z. This one is by definition, right? Okay. But m equals to 2k plus 1, which is contradicting the assumption that n even. Okay, because I said that the axiom is what? The axiom is any integer is either even or odd, right? Yeah. So it actually the or is a exclusive or. You cannot be both, either one only. So axiom. Every integer is either or even. Okay. So we reach a contradiction. And then also proof is done. Okay, so this is proof by contradiction. So yeah, okay. So what's the logic behind here? So first of all, you start with P implies Q. Okay, you start with a P implies Q statement, and then you assume P. Okay, you assume P. You also assume not Q. Okay, you assume not Q. But you get P. Okay, right? Is this what we are doing? So we got a P implies Q here. Okay, and then we assume P. We assume not Q. Okay, and then we get not P again. Right? Okay. So altogether we get not Q we have P and not P. Okay. So P and not P is what? Who can remember what's P and not P? Contradiction, right? So if this implication is true, what can imply false? What implies false is true? False, right? False implies false is true, right? False implies false is true. Okay? That means not Q is false. So you get Q. Okay? So you get Q. So this is how you prove that M is odd. Okay? This is why this contradiction here, you found that M is even, then you can prove that M minus 1 is odd. Okay? A lot of confusing face. First time seeing. Okay. Yeah. Okay. How about this contradiction here? So let's see again. So let's see. So, okay. So what was the logic here? So we got P implies Q. Okay. We assume not Q. Okay. We prove not P, which means we have not Q implies not P. So we have the equivalent statement P implies Q. So we prove the whole statement here. P implies Q. So we start with, wait. So we start with P implies Q. Okay. And then we start with not Q. We start with not Q. And then we get not P. Okay. Which means P implies Q. Okay. So maybe you'll notice that contradiction and contrapositive is quite similar. Just that we have an extra step in contradiction, which we also assume Q. We also assume P. Okay. But in contradiction, we don't assume P. Okay. Okay, we will do more question later. So maybe we will see. Okay. Maybe this one is the first time seeing also. You can, I mean, I repeat a lot of time. You can just ask question if you don't understand. Okay, so last week I promised you a classic proof by contradiction, right? Okay, so we will do it today. So let's prove that. Prove that square root 2 is irrational. Okay, let's see how this proof goes. This proof have a few steps. So I mean, have a few parts. Okay, so we prove by contradiction. So proof by contradiction means we need to assume the result is false. Okay, so suppose square root 2 is rational. Okay, so we suppose that square root 2 is rational, and then see what contradiction we can get. Okay, then since it is rational, we can write it as a fraction form, right? So I can write it as a m over n. Okay. Remember the rational number n, and m and n have no common factor. So we can like simplify all of them, right? We can just simplify them. Right? Okay, you agree? Okay, good. Someone agree. So we can square both sides. We get m squared over n squared. Okay, following. Okay, then we get 2n squared equals to m squared. Okay, So you see, so m square is 2 times some integer. So meaning m square is what? M square is what? 2 times the integer. Huh? Even, yes, even. Hey, you're only the sleeping guy and then you can answer my question. Okay. Okay, good. Okay. And then, okay, it follows that it follows that m square is even. So if since m square is even, m must be even. Anyone want to challenge this statement here? Since m square is even, m must be even. Okay, I give you another 2 minutes. Why m square even, m must be even? Okay, anyone got any ideas? Why m square is even, m must be even? Hmm. Ah, by contradiction. Did you know how to prove it? Ah, okay. Okay, good. So, okay, good. Wait, let me write down. So, okay, prove by contradiction or contrapositive. Both is the similar. So you start, both have to start with n is, you have to negate the result. So suppose m is odd. So by definition, m equals to 2k plus 1 for some k, right? So I just do the computation. So what do you get? 4k squared plus 4k plus 1, right? And then you can factorize. You got plus 1. So it's the form of odd number, right? Which is, which is odd. Okay? Proof by contradiction, proof by, so proof by contrapositive, meaning m is odd, then m squared is odd. Proof by contradiction mean assume m squared is even, also m is odd, then you get that m squared is odd, contradicting the assumption. Okay? Yep. Then what? Then continue. So in this case, this line, sometimes we will call it a lemma. Okay? So we got lemma here. So we use this lemma to prove this Square root 2 is irrational. Okay, let me write. So since, wait, okay. So m equals to 2a for some a, right? And 2n squared equals to 4a squared, which means n squared equals to 2n squared. This implies what? This implies what? N squared is even or odd? Even. N squared is even, right? This implies n squared is even. So you see, okay, in n squared is even, and then and hence by lemma n is even, right? So m is even, n is even, but I say that m and n cannot have common factor, right? So it contradicts that m and n have no common. Okay. Yeah. Okay. Following or not? Okay. So what I want you to appreciate here is how is it a contradiction? So you need to assume the result is false first. Okay. And then you go along and then you found out that your proof in the end contradicts your assumption. Yeah, this is proof by contradiction. Okay. And then you will see something, some small result being proved inside the proof. So this lemma get used inside the proof of theorem. Okay. Any question or not? Hmm? Okay. Any question? No? No? Okay. Just stop me if you suddenly think of a question. Okay, next, we will prove by cases. Okay. Or exhaustive proof. Okay. So sometimes you can break the proof in two cases. So for example, let's see this statement here. Theorem. If n is an integer, then n square equal n. Okay. So first of all, do you think this statement is true? Maybe you can convince yourself first whether this statement is okay or not. So let's say we said put 2. So 2 square greater than equal to 2. How about -1? -1 square greater than equal to -1. Okay, looks good. Okay, so let's try. Suppose n is an integer. Okay, we want to show that n square is greater than equal to n. Okay, so I prove this statement by spreading integers into greater than 0, less than 0, and equal to 0. Okay, let's say if n equal to 0, then 0 squared equal to 0. Okay, which is obvious. Okay, this is obviously true, right? If n is greater or equal to 1, then what do we get? Yeah, then we can multiply both sides with n, right? Okay, this one is by multiplying both sides with n. Okay, so we get n squared greater or equal to n as desired. Okay. Okay, how about if n less than or equal to minus 1? Okay, we get then n squared is what? N squared is always greater or equal to 0 to 1. Yeah, sure. Greater than 1. Sure. But 0 is enough. So 0 is greater than minus 1. So minus 1 is greater than. This is also. Okay. Okay. Maybe you were confused why I can just use greater or equal and here is strict because greater or equal is all statement. So if you prove one of them, you can use greater or equal. Yeah. And we also got equal in different cases. So greater or equal is fine. Okay. So this is proof by cases. Okay. How many proof? How many time already? So this is the fourth time. Okay. Okay, next. So next is called the existence proof. We also mentioned last week. Okay. So existence proof would have some quantifier, existential quantifier. So let A and B be real numbers with A less than B. Okay, want to prove that there exists a real number X satisfying A less than X less than B. Okay, so we want to find an X which is less than, greater than A and less than B. Okay, tell me what to stop already. Okay, really stop. So we will wait, let me see what's going on. Okay, coming back. Wait. Oh, you need to find me. You need to find me a real number in between A and X, given two real numbers. Wait, wait. Let me. Okay, so things is 4:53 now. Okay, so I stop here for break and then we'll come back how to find this X. Maybe you can take a break or think how to get this X. And then we will come back at 5:03. Okay. Yeah. 因为在之前那个课件上为什么会用存在，然后不是用认可？就在前面来讲，就比如这里为什么这是存在？因为 definition 是存在，它不应该是，就不可能是每一个嘛。我放3进去，它就是另外一个4，可以吗？ 就是我定了一个 n 过后，我定了一个数过后，
n 是某一个数，
对，
所以是一个符合它的。那
对，
在后面证明里面，它不那个 n 没有定下来，
但是 m 减1被定下来了 ，m 被定了，这个 m 被定了，
奇怪
怎么说
啊？
怎么说？
就以前上高中的时候，这里都一般写认取，不写存在。
没有，你先想一下这合不合理先，你先想一下合不合理，然后你再想，你先想一下合不合理先，自己想。耶，
好像是这个。
啊，对，然后可能你记错了，你可以再回去看一下。
确实当时写的一直都是认取。
你看一下，再
就
检查一下，
好像
你检查一下，有时候记错。
那个delay and delay, so I don't know what P and Q mean.
Thank you. Oh, okay. You want go first or you want to ask first?
So,
Oh no, okay. What do you mean P and Q? P, you mean this PQ?
Yeah.
This PQ is just some random
thing.
any proposition. Just,
Anything.
yeah, anything. I mean, any propositions.
Proposition.
Yeah. Do you know what proposition is? Yeah, a statement which is true or false, but not both.
就命题嘛。
Yeah.
那
Yeah. Any proposition. Yeah.
So,
Uh.
this means what?
This means what? So you mean this means what? This one. So you have this. Start with this. Okay. Assume this. Okay.
Assume.
Yeah. Assume. So meaning you have this also, and then you also have this.
Also have this.
Yeah. Also have this, and yeah, and then also have this, because from these two, I mean from this one you can get this. Okay. So meaning you got from here you got these two. This is what I wrote. You got from here you got this two. Okay. Cannot. So okay, in this example here, so I start with P. I start with not Q. I get not Q. Yeah.
Represents what?
Represent what? Oh, okay. So okay. So here I wrote P implies Q. So this one is P. This one is Q. In this case, right? And then P. Okay, not Q. So n minus 1 not odd is even. Not Q.
Not Q.
Yeah.
This P.
Yeah. Okay. And then from not Q, I got not P. Not P here.
Oh.
Okay, so I got these three things. And then I also got not Q implies, because I from not Q I deduce P and not P.
Oh.
Yeah.
So there are three. We assume there are three cases, means called P, no Q, and not P.
Yeah.
And then we prove that.
Okay. And then because this is contradiction, so this is false. But this one have to be true, right? We said that this is true, I mean. So false implies false is true. Okay. So this has to be false. So this is false, then we have Q. So we got from P to Q. Okay. Yeah.
看刚那个根号2这个。
Okay. Yeah.
对，它那个意思是说，就是如果说它是一个整数，就是有理数，如果它是有理数，它就会符合这样的一个形式。然后呢，这两个是不可以有公约数，因为它是最简化。
我可以简化它，对，
那就是它
复制
理论上应该要最简单复制，然后所以说要证明到后面说它这边就是两个同样都是偶数，
对
所以它们有一个公因数2，所以它就是不是有理数。
啊，就是对，
对
OK，
我刚刚没有，你在讲这个的时候，我没有在看这个，然后
OK，
我发现我想跟你想的一样，
啊对，
如果它一差不多就是反正法嘛，
对，
假设它是有理数的话，那它一定存在两个数值是互质的，
对，
就几何是互质的，
对，
然后就这样，
对，
那么它又是个偶数，
对，
那么 p 就等于假如是2，
对，哎，喂，什么？对，p 方等于
，p 方等于
对，
2，那你就把带进去，不对，你 p 你 p 方等于2，是个偶数的话，那你的 p 肯定也是个偶数。
这个是我证的东西，我这里证了，刚刚证了。如果 p 对是 O，p 也是 O。
对啊，
对，
我就是这样想的嘛。那 p 不就偶数嘛？
对，
所以我 p 等于 2s。把它带回去的话就是4s 方等于2q 方。
对，
所以那个2s 方等于 q 方。
对，
所以 q 方也是偶数。
对，
然后所以 O 比 O 的话肯定还有个2。
对，
所以根号2。
对，一样。OK，
我就想问这个，
就是
这一步，它有一个那个运算符号的先后顺序，那这个箭头它是在后面的，那为什么它就是整个化简的时候要先上这个箭头？
什么是叫做后面的？
就它的那个先后顺序不是要先算否，然后再算那个西序和合序，然后最后再算。
然后你的意思是什么？
因为我看到这边，这边可能
没有，你刚才是说，你说我答案是错还是什么？
也不是，就是它不是有个优先
啊，对，然后你要说是，
然后我看就是给的那个就是上节课的那个课件最后就是这道题的答案是先算这个，然后让它变成一个就是只有西序和序的那个式。
他的那个最后的意思是说，比如说，它可以，OK，不，等一下先，所以你要说的是什么？然后你说我的是我处理这个先哈，但是那个处理的方式跟你看这个先后是没有关系的。
就是等于说我是要先处理这个式子，让它变成一个可以运算，就是只有西序和序的那种。
但是和你刚才说的那个东西没有关系的。
就是所以要先进行处理的步骤，再进行运算的步骤。
对，先处理的步骤跟先运算的步骤没有关系。他的那个意思是说，如果我没有告诉你这些挂号怎么放的话，你应该要
我知道了。
比如说，可能假设啦，可能是他可能没有告诉你他是这么放的，那你就要知道这两个可能是连在一起的，他告诉你那个哪一个比较重要，明白？但是为了解决这个问题，我也没有介绍那个东西，所以如果我考试出这样多复杂的东西，我会放括弧，我会放括号。
放括号。
对，就不会说，比如说这个题目会看成这样的东西。如果我要这样的话，我会这样。对。
这个为什么？这个为什么是这个为什么是错的？
他错的意思就是说，答案是错还是对？
答案是错。
如果你要错，你就要negate它，对不对？它的negation是对的嘛？
否定。
因为这个是错的话，就代表它否定是对的。
对啊。
所以它否定的话是 there's this x not qx 嘛。所以你要找一个 x such that 这个东西是错的，这个东西是错的意思说 x 加1小于等于2x，有没有这个 x 可以符合这个？如果有的话就错。
好。那我就知道。OK，非常
OK。哎，为什么刚才不要问？
因为
为什么？
不敢说，
因为别人也有这个问题，他们不敢说，下次一定要说。OK，下次说啊。OK，hello， Let's come back. Anyone got any? Is anyone thinking during the rest or just rest? Okay, but you're supposed to rest. But so anyone got answer or not? Okay, thanks. Really? Really what? Huh? Really what? I don't know. I wrote A plus B over 2. Is this correct? So let's check. So is this greater than A? So 2A is less than A plus B. I think it's correct because 2A equals to A plus A, but A is less than B. Okay. And then next one I need to check is whether A plus B, this number is less than B or not, right? Because I need to check N. X is greater than A and X is less than B. So let's check. So A plus B is less than 2B. Okay. So B plus B, wait, 2B equals to B plus B, which is greater than A plus B, right? So because A, using the assumption, okay? So what I do is use by assumption, by assumption, okay? Hence, A is less than A plus B over 2 less than B. Okay? Any question? Okay, please ask if you have any questions. So this is another kind of proof, fifth type of proof. Okay, the next one is, I think it's very important for coding because your coding need to work for a lot of n, okay? When you run the loops and so on. So for this purpose, I prepared two examples, but this is just a basic induction proof. Okay, so this is the basic one. So the next one is the induction proof. So the sixth one, this is very important for you. So you want to check if you want to check your code is running or not, you don't need to run your code. You just write this proof down. So if this proof works, then your code will have no problem. So for example, okay, let's see what's going on in the induction proof. So I will give example, okay? Give example. So what you should see from the example is to see the general idea, general method from the example. And then you can read the textbook for the theory. Okay, so proof. So first, you need to start. So, okay, so let's see this question here. Okay, so the question here is saying 1 plus 2 plus 2 squared plus dot 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 plus 2n equals to 2n plus 1 minus 1. So let's see. Okay. Okay. So let's see what is going on in all the n. So it says that n is non-negative. So meaning n is greater or equal to 0. So first is n equals 0. So n equals 0, you get 1 plus 2 to the 0 is 1. So that means start from 1. So 1 is equal to 2 to the 0 plus 1 minus 1, which is 2 minus 1, which is 1. Okay, so true. N equals to 1, true. Okay, so this statement here is actually the what? The universal quantifier, right? So this is z greater equals 0, such that 1 plus 2. So this is the predicate, right? And then the subject. So I'm checking the true value of this statement here. How about n equals to 1? I get 1 plus up to 2 to the 1. Okay, equals to 2, 1 plus 1 minus 1. So this side is 4 minus 1, which is 3. the other side is also 3. 1 plus 2. Okay. So you can go on, right? Go on and check. Okay. But you can't check it for arbitrary n, right? Okay. So what we are going to do now is induction. So I will show you this induction here. So proof, base case. Okay. So induction need to start with a base case. So base case. So base case is starting from n equals to 0. So let n equals 0. 1 minus 2, 1, which is 1. Okay. Base case verified. Okay. Verify. Okay. And then, okay, this one is just some on comment. Don't write into your proof. Okay, don't write this into a proof. So next one is inductive hypothesis. Okay, so in the inductive hypothesis, you assume this formula is true. Is true for some value n. Okay, suppose it's true for all n equals to k. Okay, not for all, for n equals to k. Okay. And then the inductive step. So these 3 steps you need to memorize again. Best case, inductive hypothesis, and inductive steps. Okay, inductive step is we want. So this is where you need to do work. We want to prove it for n equals to k plus 1. Okay, we assume k and then prove it for the next one, k plus 1. So what am I doing? So let's see. So 1 plus 2 plus 2, 2. So 2k plus 1. Okay, so we have this. Right, we want to prove it for k plus 1. But remember that k, the case equal to k hide inside here, right? Okay. Then, so this part is what? This part, I can apply the formula. 2k plus 1 minus 1 plus 2k. This is by what? By inductive hypothesis. Okay. Right. See? So I suppose it is true for n equals to k. Okay. So I can put this in. Okay. And then I got 2 times 2k plus 1 minus 1, which is equal to 2 to the k plus 1 plus 1 minus 1, which means 2k plus 1 plus 1 minus 1. Okay. So let's see what is this. 2k plus 1 plus 1. So if you put k plus 1 here, the form here should be k plus 1 plus 1. Okay. So this is the correct formula. Okay. So this done. This is it. Okay. So I will demonstrate you in this case here. So in this case here, suppose let me see. Let me see. Okay. Maybe okay, let me see. So for example, let's say 2 to the 2 plus 2. So let me do here. So 2 to the 2 and so on. Okay. Suppose you know this, and then you want to prove it for 2 to the 2 plus 2. Okay, you want to do this. Then you will see that the previous case appear. So you just put it in and then plus 2, 3. And then from here you get 2 to the 4 minus 1. Okay. So this is a generalization. Okay. So you can prove the next one using the previous one. But the logic is you can go back and then go back and then go back, go all the way back to the base case. Okay, so the logic is like this. So you can prove the base case and then you can go all the way back using this inductive step. Okay, use this, prove it for this, but base case will prove the n equals to 1 case, and then n equals to 1 case can prove it for n equals to 2 case, and then keep going. Okay, so that you prove all of them starting from the n equals to 0. Okay, and any question for this? No? Now we will try another example for this. Okay, okay, let's prove another formula here. If how do you add 1 to n? For example, 1 to 10, how do you add them? What's the sum of 1 to 10? Okay, it's actually n times n plus 1 over 2. Okay, so let's prove this. Proof. So the base case, we start from, what's the base case? 1. Okay, start from n equals to 1. 1 equals to 1 times 1 plus 1 over 2, which is 2 over 2, which is 1. Okay, base case is correct. So we want to assume it for n equals to k. Okay, suppose it works for n equals to k. Okay, and then the inductive step is to prove for k plus 1. Okay, we want to prove it for k plus 1. Okay, so let us compute 2 plus up to k plus 1, right? Okay, but we know that by inductive hypothesis, 1 up to k, sum up to k is k times k plus 1 over 2 plus k plus 1. Okay, what should you do next? Huh? You can factorize, right? K plus 1 over k times 2 over 2. Okay, so which is k plus 1, k plus 1 plus 1. Okay, so it's in this form. So you put k plus 1 here, and then k plus 1, k plus 1. Okay, so this is the right form you want. Okay. Okay. Yeah. So this is the last slide for topic 1. Uh, any question or not? Up to here. We will do some exercises in the tutorial, and then some more example in the textbook you can study. If you are first time seeing this proof. Yeah. Who? From where? Okay. Yeah. The last K. Yeah, what's the question? Huh? Uh-huh. Yeah. This one? Okay. Yep. You mean why is it true? So A plus 1 over 2, 2, 2. So they are the same denominator. You can add them together and then you factorize. Can you factorize? Okay. Yeah. Any other question? Any other question? Any other questions? No? Now we will go into next chapter, next topic. Last chance. Hey, can someone close the door? Yeah, thank you. So I think I have to and then this. So okay. Yeah. Okay. Um. Okay. Next. We're going to the second topics. Topic 2. So in this topic, we'll learn about set, and then what else? And then functions. Okay. So to talk about function, we need to talk about sets first. So we need to have some space to work with. So definition. So a set is an unordered collection of distinct objects. Okay. And then these objects, we will call it an element. Elements of the set or members. But usually we call it a element, but I'm not sure in computer science they call member. Sometimes they use member. And a set is said to contain its element. Okay. And then in this case, we write A is in A to denote A is an element of the set. Okay. Okay. So this is A. A in belongs to A. Okay, I write it down. So A is in A. A belongs to A. Okay. And then in the other way is A. Yeah, maybe you can see this. So this way is A contains X. Yeah, A contains X. Okay. So here, distinct. So whenever we talk about set, we only talk about distinct set, distinct element. So let's see example. So example is, for example, this thing. Is this a set? No. Yeah. It is not a set. But we will touch on this again because this is something called a multi-set. When we talk about multi-set, we allow same objects. Okay, multi-set. We will touch on it. I think it's also useful in real life. Okay. So this is not a set. So another set is the set of number on the clock. Okay. What do you have? What number do you have on the clock? What number do you have? On the clock. Sorry? 4? Did I hear 4? What number do you have on the clock? 12. And then 3? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay? So I don't care about the order, okay? Because a set doesn't care about the order. Don't care about the order. Okay, sure. So this is a finite set. So also we also encounter the number, right? So the infinite number, so the natural number, the integers, the rational, and the real, and the complex. Okay, last time we introduced this in the domain of discourse. Okay, the domain. And then next, what do we have? Okay, this one also is very important. So this is intervals. Okay, intervals typically we look at the reals. Okay, so in reals we have closed intervals. Okay, closed interval A B equals to the number that are greater or equal to A, and then and less than or equal to B. Okay, and open interval. The open interval is strictly greater than A and strictly less than B. Cannot include A and B. So we put a round bracket. Square bracket meaning we include A and B. So we can open. These are the open, close and open interval. Open, okay, interval. Okay. So one you can include include B. The other one you can include A but don't include B. Okay, this is the closed. Okay. Another notation you can see is something like this. Okay. You put the square bracket the other way around. Okay. Okay. Yeah. So yeah, only in real we have this interval. Because if you imagine this real line here, so this is 0. So if you look at the okay, so maybe I tell you a bit the relation between natural number, the and then rational, then real. Maybe C. You want to hear relation with C? Maybe okay, I edit it for the sake. So okay, so natural number is discrete. So there are one what? One one what? One unit, one length. Okay, one length apart. Okay. In higher uh, max term is metric, but anyway. So we can go to the right, we also can go to the left. So we got direction left. So next, and then we got fraction. Okay, we got fraction. Okay. So just now we proved that for every two real, we have another real in between. So every two real, we can have another real. So every two real, we can have another real. So also these both are filling with the irrational. So that's why we got a line here. That's why we got a real number line. It's not discrete anymore, but a line. Okay. That's why we got a line here. That's why we can draw a line here. We are not drawing like this. Okay. Because these spaces are filled with rational and irrational number. Okay. So actually it's a line. And then C, if we want to add C in, we can add this minus I in. So it's actually a close up. Yeah. So we start with point, and then we become a line, and then become a plane. Okay. Yeah. Okay. Yep. So this is how the set sitting inside each other. Okay, they sit in each other. So of course, if you say that, isn't that this is another real line? Yes, this is another real line. Yeah, they are, I mean, isomorphic or anywhere, but you can see this as another real line. Actually, here there's another real line as well. Here there's another real line as well. Yeah. So there's different way of the set sitting in each other. Okay. If you're interested in this, you can take some more pure maths course. Okay, next 5. We can have set of set. Okay, the element itself is a set. So this is, for example, I can take the set of integer, the set of set integer, natural number, rational. Okay, so in this case, the set of natural number is an element of the set. Okay, but one is not an element here. Okay. Yeah, the element can be a set itself. Okay. Okay. Next. What do we have? Next. So we have the empty set. What if this space has nothing? Okay, we have this set. Okay, we call it an empty set or the null set. Okay. We say that the 0 slash is the set that has no element. Okay. Okay. Last time I told you that we can build natural number using set theory. So in this case, I want to show you what are natural number to them. Okay. So they will say that empty set is the 0. And then the set of the empty set is 1. And then the set containing the empty set and the set of empty set is 2. Okay. So you want to guess what is 3? The set of what? You want to guess? Anyone have a guess? Can guess the pattern? Huh? Anyone got any guess? First of all, it contains 0. Second, it contains 1. And then it contains 2. And then we keep going. 4, 5, 6, 7, 8, 9, 10. And then we okay. So we understand 1 as a successor of 0. and then 2 as a successor of 1, and then 3 as a successor of 2. So it's a adding on, adding on, adding on. And then all the addition or multiplication we can study using this successor function or operation. Yeah, but that's another whole theory. We won't touch it here, out of the scope. Okay, out of the scope of this class. So I just want to show you that there is a set that contains empty set. Okay, must remember this. It's possible. Okay, so we have so many set in the world. So we want to see when are they equal to each other. Okay, so let's see when are they equal to each other. So two sets. Like for example, last time we talked about the logical equivalence, right? We have two propositions. So we want to know whether when are they equivalent. Now we have two sets. We want to see when are they equal to each other. So they are equal to each other if only if they have the same element. Okay. So how to check in practical? So therefore, let A and B be any set. So A and B are equal. So I write A equal B. So equal here, there's a lot of meaning of this equal. So if I say the number is equal, then that means they are equal. The equality is on number. So if I say equal between set is a set wise equal. Okay. So they are the set. So I'm going to define if and only if for every x in A, x is also in B. Okay, if and only if. So you take an x from A and then show that it is in B, and take an x in B, show that x is in A. Okay, we will see the example. Okay, we'll see example. So for example, we want to see whether these two set A, this is A, this is B. Okay, are these two the same? Huh? Yes. Okay. Want to show. Okay, I will write WTX. Want to show A equals to B. So I need to check for every element here. It is in here. So for example, 1 and 2 is in A. Is 1 in A? What is 1 in B? 1 in B or not? Is 1 in B? Yes. 2 is in A. 2 is in B or not? Yes. Okay. So yeah. Okay. And then also I need to check if 2 is in B, 2 is in A or not. Yes. 1 is in B, okay. 1 is in A or not? Yes. Okay. So they are equal. Okay. Actually, there's another concept here. So there's a sub concept here. Let me write it out. So definition. Then no, then the set A is a subset of B, and the other way is B is a superset of A. Okay, if and only if this is one direction. So for A in A implies A in B. Okay, and then we will say A is a subset of B, or B is a superset. Wait, the other way, superset. Okay, so subset. superset. Okay. So in this case here, we will write this step. We will write A is a subset of B, B is a subset of A. Okay. So together, this implies A equals to B. So you can think of this subset like less than equal to. Okay. But we will make this connection precise later, which is the cardinality, the size of the set. Later we will introduce this notion again. Okay. So for example, remember the clock, the set of clock numbers. The set of clock number is a subset of natural number, right? So 1 to n. But n is not a subset of the clock number. Why? 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 Why the natural number is not a subset of the clock number? Remember what's the clock number? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So why is the natural number not a subset of clock number? 0? Yeah, okay. 0 is in n, but 0 is not in the clock number. Okay? Or 13. 13 also can, 100 also can. Okay? Yeah. Okay. So see, so remember the revise the predicate logic. So if you want to show that this is false, that means there exists an A in A such that A is not in B. Okay. The predicate logic, the quantifier. Okay. That's why we take the logic first and then we break here. Any question? No? No? Okay. So the first theorem, yeah, we're gonna prove here is we want to study the subset of every set. Every set. So every set, the claim here is every set X must contain at least 2 subsets. Okay. So to make sure this subset is not, how to say, it's not it's not just for fun. Okay. Every set have at least 2 subsets, namely the 0, the empty set, and the set is. Okay. So want to show what? Want to show empty set is in X and X is in X. Okay. So we will prove using direct proof. Okay, we'll use direct proof. So let's show the empty set is in X first. So to show that is in X, by definition is what? Then definition of subset is every set in A have to be in B. So every element in the empty set, we need to show that A is in X. Okay. Okay. So A in empty set, what is the definition of empty set? The set that contains no element. Okay, so this is false, right? There's nothing here, but so this is false. False implies true is true. So this statement is vacuously true. Okay. So we will say this is vacuously true. So let me write out the whole thing. Things V has no element X in A is always false. So the conditional statement is always true. Okay. Which means X is empty set is a subset of X. Okay, next. Okay. I also want to introduce this word. So in this case, we say the statement is vacuous, vacuous, vacuous. Okay. Okay, next. Next, we want to show X is a subset of X. That is, for every X in X, for every X in X. Okay, maybe I use different way to write it to show you. X in X, X is in X. Confused or not? Huh? Confused? Confused. Okay. Okay. Actually, this is the how to say? This is a valid way to write it. So, this is equivalent to for every X. X is in X. So, how to read this sentence is for every X. Okay, I need to tell you what's the domain of discourse. I think there's some problem in the book. Sometimes they don't write domain of discourse here, obviously, but I want you in this class to always write where this domain is. Okay, in the book they present it in this way. I prefer this one. So for every X, you need to tell me where the X live first. Okay, and then the statement S has to be in X. So in English, okay, English, for every X in X, X is in X. Okay, this is English. Okay. So I think this statement is clearly true. You agree? For every X in X, you take it out, it's always inside X. Okay, agree? Anyone want to object? Agree? This is really true. If you can't see it, you should voice out because it's clearly true. You should voice out if you can't see it. Maybe you have some wrong idea. Okay, because in mathematics, sometimes when people say it's clearly true, you think that you can't see it. It is mostly because you have a wrong idea. You think a different way, or you got different condition, but actually the condition doesn't exist. Okay. So the other way, yeah. So we will say that another definition: the set A and B are equal. Okay, if A is a subset of B and B is a subset of B. So as an exercise, prove the two definition of equal set are equal. Okay, equivalent. Equivalent. I'm going to use equivalent. Equivalent. Okay, proof. Okay, make sure the proof. Okay, maybe I stop here then so that we can prepare, take a rest and then prepare for quizzes. Not too many stuff going on. Okay, any question or not? Any question? If not, we break until 6 o'clock and then we come back for quiz. Yep.
一个集合的真子集是肯定是要是一个集合的，
什么？真子集？
就是这些人。这里缺的那一排，这个是一个非空集。
啊，不是啊，空集啊，空集是空集的就啊，
那它不差一个
对对对，嗯，是吧？
是怎样？我不知道它的英文，但是它表达应该是这样。
啊，对对对对对，我本来想要，哎，没有说呢，对我还没有，我对对对对，
那是不是空集的正子集还是
不不不不不不不不不不不不不，这个是叫做 proper subset，对，这个叫做 proper subset，但是这个不是 proper，懂什么意思吗？就是这个和这个的差别啊，对对对，
但是这个东西它是不是就是说一个东西的非空子集、非空真子集一个正就是一个集合的真子集，它肯定要是一个集合，然后空集的真子集不存在，所以空集的真子集是一个不存在任何元素，然后又是集合的东西，那不就是空集？
那所以是
所以空集有两个子集吗？
空集有没有？嗯，所以没有两个子集。
空集有什么有两个子集？
嗯，但是这两个没有说是 destroy 或不 destroy，不是一样或不一样，对不对？对不对？他没有说他们不可以，他们通常如果我们说它不一样，我们会叫做 distinct。
一样的。
因为他说嘛，因为这个如果你拿 x 等于 phi 嘛，这样这个就是 phi 和 phi，对不对？对吧？
对，我觉得
但是他没有说是 distinct 啊。
那所以这个是成，它有，那所以它的空集的这个是没有，就是还是空集，还是
对呀、
还是空集。
就看一下，我看一下那个 definition，希望我没有讲错，我看一下。对对，因为它符合这个 definition，所以如果这个是对的嘛，这个跟这个的原因是一样，但是这个的话，因为你也不能够查，喂，等一下，所以你这个也要对，因为你要找出一个，但是你找不出嘛，因为没有东西在里面，
对的，空
这个是错的，所以和一个错的东西的话，它就是
就是
错的，
错的，
那就没有了，
所以
没有，
空集的这
没有，
个是什么？没有，
没有，
就是没有，就是没有。那没有就是空，那没有不是空集。
没有，是不是空集啊？喂，等一下先，怎么可以这么绕啊？你说没有的话，但是一个没有的空集就是
一个没有的集合就是空集了呀，那就是它的
又绕回去了，
对呀。
这么神奇。 这么神奇啊？
对，破水晶。
要想的，要找的，有这么神奇的视频，没有想过，给我想个，没有想过。
我要问这个2S加1是想
只想因为哦，这个是说我要 prove that m minus one 是 odd 嘛？的意思就是说会有一个integer，
我可以用回 K 吗？
不可以，因为这个 k 我已经选了，因为我
另外一个 step 嘛，要再用另外一个 variable
不一样的东西，因为我已经选了那个 k，
但如果我用2S 减1可以吗
2x 减1哪一个？
就这个，因为它是加1嘛。如果用2S减1，不就直接相等了？
不可以，因为我的 definition 是说，我的 definition 是
好像没有拍到。
因为我的 odd 的 definition 是加1啊，当然你可能有一个 definition 是减1啦，but 我的 definition 是加1，所以你一定要回来这里。对，
就是要跟我们原版。
对，因为这样你才知道它是 odd。对，可能你可以 prove that 减1是 odd，加1也是 odd，那你就可以这两个互换咯。
咱们做 quiz 的话是电脑上做还是
用纸做？
用纸做
对，用纸做。
？Teacher,
Yep.
I want to
嗯
move the courseware before this.
Yeah, this one. I mean this one. Thank you. I will upload the lecture note on Thursday. I'll upload the lecture note on Thursday. I'll upload the lecture note. Upload. Yeah. Download, download.
Or review the.
I will upload to Moodle. Are you in the Moodle? Are
Yes.
you in Moodle? Yeah. I will upload to that on Thursday after my last class. Yeah. I will upload.
Teacher, but I still
Okay, what?
don't. I still don't.
Understand?
We assume
Yeah.
P is uneven.
Yeah.
Not Q. Q is M.
Minus one is odd.
Yeah.
Then and then
Not Q is M.
is even because of the axiom.
Because of
The axiom.
axiom.
Yeah, that's the axiom. Yeah, and then
Then not P is M is odd.
yeah.
Then we can what this means.
Not Q.
Not Q
Imply.
Yeah.
Are you here last week? Last 2 weeks?
No.
No, you're not here. So you just arrived.
You
just arrived. Just arrived.
This right? Yes.
Yeah. Oh, okay. Yeah, last week. This one is last week material. Imply. First day last week. First week, second week. We work on this imply. Yeah. So from not Q, we can get P and not P.
Not Q is
Here. Yeah.
Not Q is that.
Yeah.
We can't get Q.
We mean like GQ.
But we can get
P and not P.
not Why not Q can get P?
Because we assume P is true.
P
Okay.
is true.
Yeah, because we assume P is true, so I can put true statement here.
Statement here.
True statement.
If P is true,
Yeah.
so not Q is false.
Not necessary. Not necessary. What do you mean? What do you mean P is true, Q not Q is false? Why not Q is false? Why not Q is false?
Because we assume P is true.
Okay. Maybe we discuss later because it's 6. We wanted to first. Last, you want to ask? Last question. Is it fast?你只不过证它是等于 T 或者用 truth table。为什么？Yeah，你只能够证这整个东西是 T，这个 reduce 成 T，或者这个的 truth table 所有是 E。好问题。我可以给你听，你就是用 commutativity、associativity 跟 associativity。associate 去看那个 table，这个 table 呢？associate 或者 commute 就是可以左右交换，或者可以先做前面，先做后面，用这两个。为什么你刚才那个上课就是先不要问的事？
那个其实我有一些其他的都没有来，
对呀，就问，
有很多，所以说
问不了。
要不起我进入这两个有时间的，
对呀，
只能先问课。
不是，我是说刚才一开始我不是给时间你们问问题吗？
对呀，
为什么不问？
为什么想问？
问啊！他们不要问你就问啊。对呀，不然你就失掉你的机会了。
那我可以
下周，下次我问。好，用这个和这两个。不过我暂时不会告诉你怎么用啊，你先试一下。好。OK，I need volunteer from every group. I need the first guy. Every group, can I get 4 person and then count how many students in your row, and then collect the percentage for me, and then count it down. Huh? 21. I need to write down the number. How many of you? 21. No. Okay. 21, huh? 21, 15, huh? 15. Okay.
我们那一列是6个。
No, I mean the whole
全部。
18, huh? Okay. Just 18. Okay. 15. Because I need to calculate how many of you. Yeah.
要发下去吗？
发下去。Okay. So if you don't understand the KFC in case you don't understand what is KFC and Mama, I put definition here for you. It's just two restaurants. But if you don't know the restaurant, it's okay. It doesn't affect you answering the question. And then also there's a typo. The typo here I want to make is hint. So first question under the hint, actually it's hint for 1.2. Because actually I make longer question, but I remove some of the questions. Enough? Huh?
The wrong way of switch play. 20.
20. Switch where? What do you mean switch place?
Disappear.
Huh? Disappear? Disappear. I don't think so. They are all correct. Did you calculate wrong just now? Huh? 20, ah? Huh? You didn't get paper? Huh? Why minus 1? 1, 2. Yeah, correct. 20. 20, correct. 20. So 20, 15, 15, 18. Okay, you don't discuss with your friend and then don't discuss this question. Because got other group. So this question only you and me. I want to understand whether you understand the course content or not. So we will stop at 6:26, but you can submit earlier. If you finish earlier, you can start doing tutorial. I will collect all the paper at 6:26. Yeah, what's going on? What do you want? Pen? Okay. Do you have any friend that can borrow you pen? Do you have any friend that can borrow you a pen? You can ask. Huh? What? Okay. Here. Yeah, I'll tell you. Make sure you return the pen. Hey, why got photos one? Huh? Hey, who take the photos? Hey, okay, don't post. I mean, okay, at least for this, okay. Don't disseminate this question until I finish all the exam because I still have online exam. Okay, because they are COVID positive person and also visa problem, so I have to give them how to say. I have to give them online quiz. Yes, don't disseminate this question first. Okay. Don't disseminate until I give back the marks. For now, only keep between you and me this question. So that means you leave this class, you forget the question. Yeah, cannot discuss this question anymore. until I give back the marking. I still need to arrange online quiz for them. Okay, there are two typos. There are two typos. So second question, task 2.1, it actually just English. So show that they are logically equivalent, not equivalents. Are logically equivalent. Okay. Equivalent, not equivalent. Just English. Okay. Logically equivalent for the second question. Hey, why someone is looking at the phone? Why are you looking at the phone? Huh? Hey, don't make me do rules that I want you to keep your phone again. Okay? Please be active. I want to make a lot of rules, but please be honest. Okay? Close all your electronic devices. Yeah. Um, yeah, okay. I will finish the work. Yeah. Maybe there's miscalculation of the work because I changed the question in the end. So maybe question 1.3 or 20%. Okay. Close your computer. Close all your computer. Please be honest. Close your computer. Not just close it down, it's okay. Close it down. Close it down. By the way, remember to write your name. Write your name and your student ID. Write your name and student ID. Try your English then because your record is in English. Hey, write your student ID in case there are students in there. That's okay. If you haven't done, you still have 4 minutes. Hmm. Okay. Hmm. Okay. Go. Okay. Hmm. Let me check the number. Okay. Okay. Mhm. 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 Okay. Mhm. Thank you. Thank you. Thank you. If you haven't done, you still have 4 minutes. Don't discuss first. There's someone still doing. Yeah. Don't discuss first. Someone else are doing. Still doing. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Hey, this one no name. DMT 220. DMT 2209247. What's your name? Hmm? Name. Name. Is it there are two more? Two more? Or one? Is there another one? Okay. Please keep quiet first. Okay. Time stop. Time stop. Okay. Okay. Yeah, actually, I wanted to discuss this quiz, but I can't do it now because there are some students that got COVID, cannot come to class, and also visa problem. So, so once you leave this room, then please forget this question. Okay? Don't tell anyone, and then until I give the question back. And then what? Okay. So actually, the second question I meant to ask you to demonstrate whether you can do the truth table or not, but since I didn't put it in the question, so I will change for the others. But for now, maybe I'll adjust the marking for this group because actually I wanted the answer in truth table only. But since I worded, my wording is not clear, so but for the next two classes and then the other, I will change the wording for the second question. Um, okay, so please don't tell anybody and then don't discuss among yourself after you leave this room, okay? Otherwise, you will get doomed, okay? Okay, so let's do the tutorial question for today. Okay, we will start in 2 minutes, okay? I just run through the solution later. Maybe longer, maybe we start 6:35. 6:35. Okay, we start in 6:35. You can do it, try it, discuss with your friend. With the tutorial. Actually, I forgot to mention to you the induction is in 5.1. Yes, if you want to have a reference, is 5.1. The chapter. Hello? Okay. Maybe we will open. Okay, just open. Hey, why someone wrote Chinese in your answer? You don't think I can, I mean, I can read Chinese, but I can't accept Chinese as an answer. Okay? So don't write Chinese explanation. And I also quickly run through the solution. I was looking, see whether you got some interesting predictive proposition or not, but someone changed my better to big. I don't change my adjective, but if you think big is better, then I accept. Okay, this is just quiz, so I will accept. Somebody got right, 140 times, 104 times better, something like that. Okay, I was thinking like someone can write maybe KFC's or Mama is better, and then and or something like that. Um, yeah, that's fine. Never mind. Okay. Okay. Let's look at this tutorial question. So, okay, this is a bit like this question. So, if S is positive real, then S squared is positive real. Implies if S squared is positive real, then A is real, which is false, right? So P implies Q has nothing to do with Q implies P. Okay. So next one is x not equal to 0 and x in real, then x is not 0. And then if this is true, yeah. So if A is in R and A squared not 0. Hey, did I copy the wrong question or not? Did I copy the wrong question? Oh no. So they are exactly the same thing, right? So just swap these two. Okay. I thought it's some contrapositive, but just P and Q implies R, and then Q and P implies R. Okay, commutativity. Okay. And yeah, this question here, last week, if you remember, there's a question on this, and then we give a counter example. And then here is some attempt to prove that it is true, but the law is false. Why is it false? Because if it's all, then you can't deduce PC or QC. Okay. This step is false. This step is also false because it's taking PC or QC from all. Only PC and QC, you can deduce PC. Okay, if N you can deduce, if all cannot. Okay, and then this one, you have to go back and try. One advice I can give you is to use the instantiation. Okay, pick example, and then use the implication to conjunction formula, and then use some associativity, and then idempotent, so on. Okay, try, and then I will put the answer up on Thursday, and then you can check. And then this proof, okay, so prove that the product of two odd integers is odd. Okay, direct proof. So write down what's the definition of odd. Okay, and then multiply them together. Okay, and then show them it's actually odd. Okay, everything from definition. So there's, I mean, 2 steps, 3 steps. So start from definition, multiply them, and then show that it's an odd number. Prove that if n is an integer and 3n plus 1 plus 2 is even, then n is even. Okay, so first one is to use what proof is this? I didn't write it down. So this is contra. This is a contrapositive. Yeah, this is a contradiction. So from my proof, you should be able to see whether how I prove it. So in this case, how I see that it's a contrapositive, because I assume that n is odd, so I assume the negation of the result, and then I prove that the assumption is odd. And then contradiction, I need to assume the assumption and the negation of the result, and then show that actually my assumption contradicting my assumption. Okay, so one one skill you can learn is read the proof and then decide which method. Okay, this is another skill you can learn. And then yeah, this one also direct, so similar to what we discussed in the class. This one okay, this one is to prove if and only if. So 2 direction, go to here and then go backward. Okay, so I claim that go backward is easier. Okay, you just start from here and then you show this, start from here, show this, and then going forward, you can use the factorization. Okay, these calculations are just high school calculation, but to write it, okay, write the proof. Okay, so this one show that 10 is not square of a positive integers by cases. I think the book gives you the hint. So basically, it the cases will help you split into 2 cases. One case is less than 10, one case is the square is greater than 10. Okay, so that you don't need to write every number out. Okay, and then F 1.8.16 is to prove or disprove. Okay, the question is prove or disprove. So this question, the hardest part is to decide whether this is true or false. So you, of course, by experience, you can see it fast, but if not, you need to be a little bit creative. Okay. So actually, this is false. So if you take A and B rational, then square root 2 is actually irrational. We already proved that square root 2 is irrational. Okay. And then one sub, actually it's 3.8. I don't know. I think I've already changed it in the model. So it's 3.8. I always pick the even one. So it's to show the contrapositive, you can get the answer easily. And then 1.5.1.16, okay, is to show another formula, is to multiply the consecutive three numbers and then add them up. And then we have this beautiful formula here. So since it starts with 1, so base case have to be 1. And then suppose it's true for n equal to k, and then we want to show it for n equals to k plus 1. So do it until k plus 1, and then show the formula is true when you substitute k plus 1 in. Okay? So it should come out nicely. 5.1.32. So this one, the question is about division and also prove it by induction, because it is true for all n in the integer, so prove it by induction. So when this is 0, so everything divides 0. Okay, so this is always true. And then secondly, suppose it's true for n equals to k, and then prove it for n equals to k plus 1. So you sub k plus 1 into it, and then try to find back your inductive step, inductive hypothesis. Okay, so you need to go back and find this form here. So you need to make sure, so you need to find this form. So I found the form here, and then the rest is like this. So by inductive hypothesis, when this is k, this is divisible by 3. Okay, the rest here is divisible by 3 as well, because I can factorize the 3 out. Okay, so the whole thing is divisible by 3. Okay, yeah, that's all. Any question? Any question? Any question? Any question I can discuss? If not, can dismiss. Before we dismiss, forget the quiz question. Okay, forget the quiz question.
我就是写中文，我是你看，我怕我写就是英语写高水句。但是你写中文我也不会看的。还有英语能写。对。我怕我写不够准确。但是我是说，不管你中文写的是什么都不会看。对。可以吗？可以啊。可是怕当时不错了。对，就告诉你这样。不好意思。不会。那个要用，到最后手要用，那个到最后手要用。对，把它调好过后，才可以。对。然后当时就是用这个，像这个问题的课本上不好，我等这个。
一个感叹号登场，是什么呢？
我想说这个左右，这个左右是可以证明为什么这个是一个人。
兄弟，兄弟，
对，就是
我笔还在那里
从。这里过去，从这里过去是怎么样的？就是为什么他们是一个人？用句子来prove。
用句子来。
对，用句子来。
那它这里的 demo 跟 demo
对，
就是